Okay, so I just wanted to summarize the proof by induction there that we finished in the last video, and then the screen went a little crazy. So the induction principle is if we want to prove a statement is true for all positive integers n, and it's a two-step process. The first step is to show that the statement is true for like n equals 1, and then the second is a kind of a connected set of statements. We assume the statement is true for n and show that this implies it's true for n plus 1. Okay, and then as an example, we prove the statement about the sum of the integers from 1 to n. And so this is an example of a statement that depends on n, right? And so we proved it for n equals 1, and then we went through the details of the rest. Okay, so we're not going to do a lot with induction, but it does come up in chapter 5, so I just wanted to mention that. Okay, so let's try an example of something called a telescoping sum. So in a telescoping sum, many of the terms are going to cancel out, and so it's easy to see if you actually write down a few terms of the sum. So here's an example of a telescoping sum. There's some more in the homework. We'll use n as our index this time. Okay, and so let's see why this is called a telescoping sum. Let's go ahead and write down what our sum looks like. So for n equals 1, we're going to have 1 over 1 minus 1/2 plus, and then for n equals 2, we'll have 1/2 minus 1/3 plus 1/3 minus 1/4. Are you seeing what's happening? Plus 1/4 minus 1/5 plus 1/6 minus 1/7. Oops, I skipped one. Plus, maybe I'll put it down below here. Plus 1/6 minus 1/7. Good. And so are you seeing what's happening? Minus 1/2 cancels with plus 1/2. Minus 1/3 cancels with plus 1/3. Minus 1/4 cancels with plus 1/4. Minus 1/5 with plus 1/5. 1/6 with 1/6. And so what we're left with is the beginning, or the first term, minus the last term. And so the sum then is really easy to compute. It's just going to be 1 minus 1/7, or 7 minus 1 over 7, or 6/7. Good. And so that's an example of a telescoping sum. So a telescoping sum is one that collapses once it's all extended. Okay, which means that many of the middle terms will cancel out. It may not be all of them, so you kind of have to be careful about looking at that. Good. All right. So I'm going to pause here and just I'm going to open up my book and just we'll try a few random homework problems. Okay, so here's one. By the way, on page A37 there's some formulas that we can use while we're working on our homework, and so I've written a few of those down, and let's take a look at number 31. So in this case we want to find the value of the sum I squared plus 3i plus 4, where I is running from 1 to n. Okay, so the solution, first remember that if I have the sum of ai plus bi, I can rewrite that, right, as the sum ai plus the sum of bi. So I can reorder the terms of the sum, and so you can see why I'm bringing that up now. Let's go ahead and feed the sigma notation through, and so, or distribute it. I equals 1 to n of I squared plus the sum I equals 1 to n of 3i plus the sum for I equals 1 to n of 4. Good. And now this first one is ready for a formula. I'll just go ahead and, maybe I'll rewrite it over here. I didn't want to put an equal sign here, but I guess we'll go ahead. Let's go ahead and put equals. Okay, sum of I equals 1 to n of I squared plus, I can factor out that 3, right? And then I could factor out the 4 if I wanted to, or I could just leave it as 4, but that'd be a 1. Good. And now, are you looking at the formulas up here? So for 1, right, I get an n. Oh, let me not write that in red. That's hard to read, isn't it? So I can replace the sum here, oops, with an n. I can replace the sum of I, right, using this formula. So this is going to be plus 3 n times n plus 1 divided by 2. Well, I could say it's 3 times this, right? Oh, let me write this bigger so you can see. Okay, this is 3 times n plus 1 divided by 2 plus 4n. Good. Plus, and then I squared. We can put this formula in here. And so that's going to be n times n plus 1 times 2n plus 1 divided by 6. Okay, and so this is our final answer. Now, we could try to combine these terms, but in this case it's really not going to give us any better expression, so we'll just go ahead and leave it in that form. Good. All right. Let's see, maybe I'll pause here. We have time for one more problem, so let me pause here and I'll find one in the book. Okay, this is problem 14 in the book. We want to write this expression using sigma notation. And in fact, let's see, I think I want to force you to do something. I want to force you to use sigma with I equals 0 as the first index. So that means, just to give you a hint here, this is I equals 0, I equal 1, I equals 2, and so on. So you might pause the video for a second while we figure this out. Okay, are you back? So let's see, I need to get to 3, so I think I plus 3 in the numerator. And let's see, checking those, that's 4, that's 5, okay, that's good. Divided by, this is, looks like all the time, the denominator is 4 bigger than the numerator, right? So if we take I plus 3 plus 4, that should do it. And so that would be I plus 3 over I plus 7. Good. And so we can write this then as I plus 3 divided by I plus 7. And now we're starting at 0, but when do we stop? Let's see. Well, this is 3 less than the value here, right? This is 3 less than here. This is 3 less than here. And so we would stop then 3 less, so 20 terms, or I equals 20 would be the stopping index. Good. So there we go. So notice, by the way, probably the more natural thing to do would have been to write this as like k equals 3 to 23, right? Then you would just have k over k plus 4 or something similar, something equivalent. Very good. So the section on sums is pretty short. You might read over the section on the principle of induction, but that's really for a little bit later on, so it won't be on the test, but we will be talking about it later, so it's good to at least give an idea of what's happening there. All right, I'll see you later.